Good afternoon, ladies and gentlemen of calculus. Welcome to room 15, where?
Learning never ends.
Where it never ends. Yes, we were talking about volleyball game. Since learning never ends, it doesn't even end during volleyball games, does it? So we had calculus during the game, and we had these fans here. We did a fantastic job of calculus during the game.
I know.
And they did integral calculus, no less.
I did a fantastic job at screaming. Not so much.
Fantastic. So anyway, yes.
But I was screaming drastically.
So that's good.
No.
There'll be other opportunities. Okay. Today we're going to be starting on our package. Before we do that, we're going to get to something called the calculus roller coaster. Now last Friday, we did La Maison de Calcul, where we did the 3-story house and did the relationship between f of x, f prime, f double prime, and so forth. Today we're going to be looking at something called the calculus roller coaster. And basically what it is, it's a roller coaster that represents a placement on a coordinate plane. In this coordinate plane, and I'm going to sketch this and draw a few things. So we're going to make a coordinate plane out of this. Kind of an XY coordinate plane. So I have a little shaky hand from resetting the touch TV with the muscle man a little earlier, but that's okay. So anyway, we got an XY coordinate plane, and what we're trying to do with the calculus roller coaster, we're trying to find the slope at a point. And what happens is the slope at a point. Is it going to be, I'm going to make it red. Is it easy to find the slope at this point? Okay, what we have is something here. What we're trying to find is we're trying to find the slope right at that point. Does that look like it's about right? Pretty close. But what we do in calculus is we find exactly what that is. Up until now, I will show you what you've been doing. Up until now, you've been taking this point right here and a point right here on either side of this point, and using those 2 points to create what we call a secant line. So this is called a secant line, not to be confused with the trigonometric ratio secant. This is a secant line. And the secant line is created when you have 2 points. And you take those 2 points, and what we're doing in calculus is through the limiting process, we are taking these 2 points and we are making them infinitesimally closer. And so if we draw 2 points that are closer, we can use these next 2 points and draw another secant line, which, though still not the slope, the line at that point, it's closer. And what we do through the limiting process, we get it till infinitesimally closer until the line comes right, and I'm going to take this line and move it, will be right here. And when we find the slope of the line at that point, it ceases to become a secant line and then becomes what we call a tangent line. And one of the things we're going to be doing is finding the equation of a tangent line. So again, I'm going to go ahead and take this. I'm going to go ahead and take this and clone it. Clone. There it is. Clone. I'm going to take it. So here's our original secant line down here. Here's our secant line. And through approximation, and by the way, one thing we're going to do in calculus, we're going to use estimating methods. We're going to use sometimes a secant line or an average rate of change. The secant line, the slope of secant line equals average rate of change. So slope of secant line equals average rate of change. And it, just for conveniences, a lot of calculus teachers don't like doing this, but I like doing it because I think it's a helpful acronym. That what we can call this is AROC. So AROC is an acronym for average rate of change. And when you use the average rate of change, you're not using calculus exactly, but you're using what can pass for it for a calculus approximation method. Because you can see that the closer we get, if we get really super close, we'll have a really good estimate of the slope of that tangent line, even if not exactly. But the invention of calculus gets it exactly. And the same with this, now Friday, we got, Thursday and Friday we got it exactly because we knew the exact area of the geometric shapes. Same thing at the volleyball game the other night, right? You knew the exact measure, the exact area of that triangle, didn't you? Which was 3 by 3 and then divided by 2. You knew it was 9 over 2. And so that was the area. But we're going to have equations that are more complex where you really can't do that. One of which is on one of the calculus t-shirts, right? The integral from 0 to 1 of x cubed dx. And so we have that. So anyway, I'm going to go ahead and put some little words here. So the slope, okay, slope of tangent line there are different ways of saying it, equals first derivative you remember on the maison de calcul we talked about first derivative, right? Or sometimes, like if this function here, if we call this function here f of x, the equation of the tangent line is called f prime of x. Sometimes you'll see it written like this, d dx of f of x. That's supposed to be f of x. F of x. So when you say d dx, that's the first derivative. D over dx equals f prime of x. Another thing is this first derivative, f prime of x equation equals the slope generator equation. In other words, you get an equation for which you plug in x, you're not getting position anymore, but you're getting the slope at that point with the equation. Okay, so you can just plug that in. And so there are different ways, there are probably ways I'm forgetting right now, but part of what we're trying to do in calculus is build our vocabulary to remember what they all are, because they can be called different things. And I'm going to tell you one thing that we have before we get on to work on a packet. There's something we have that's called PVANG. Anybody ever heard of PVANG? I'll show you. Okay, there's an acronym. Where is that thing? There it is. Okay, PVANG. Okay, it's got to help you remember what we're trying to do. I'm going to put it like this. PVANG. Okay, does anybody have an idea of what those 5 letters stand for? Okay, I'll give you what they stand for. And these stand for the 5 different representations of calculus we're going to go into this year. And they'll make sense. The first thing we look for, P, means physical. So a lot of times the representations we have in calculus are physical. Like I mentioned the other day, I mentioned object that's thrown into an air, right? A physical thing. And there are other physical examples over the year we're going to have as applications for calculus. Okay, the next thing we have physical. Next thing, V. What does V stand for?
Velocity.
Velocity is a good guess. Actually, that would be, velocity would be a perfect one when we have position, velocity, acceleration, like la maison de calcul, right? But in this case, what we're talking about verbal. Like a verbal explanation of what's going on, right? To say it in words. Verbal. My pen is a little glitchy. I have a new computer here, and I did it to get it not as glitchy. Okay, what does A stand for?
Yeah.
Okay, sometimes it could be algebraic, or sometimes you call it analytical. So I'm going to give both of those. So analytical would be like an equation. And I'm going to put algebraic because they're somewhat similar. And what's N going to be? N stands for numerical. And usually it means a table. And then what does G stand for?
Geometry.
It's related to geometric. I'll tell you, it's graphical. Graphical. It ends up being geometric too, though, because when you think of what we did last Thursday and Friday, that was graphical, wasn't it?
Yeah.
And then most of the time, just like in the history of calculus, most of the energy, the mental energy, gets focused on this thing right here, working with the equations and all that. But I want us not to forget that these equations we use and manipulate can represent physical situations. Okay, so bring us to it. And then the graphical, one thing you have that's really a powerful tool at your fingertips that I didn't have in my day when I was working on calculus is that graphic calculator. We're going to be able to go and see that. And also the numerical aspect with those tables. So this numerical is going to be most of the time with tables. And we're not going to see a physical, for most of these things, we're not going to see a physical relationship, but we have to remember that the invention of calculus and really just about everything in mathematics we can think of was created in response to a physical, real-world situation. And so it has application, or has had in the past, and will in the future in ways that may not have yet been invented. And as young people today, you have the opportunity of being some of the inventors of that. I have one of my missionary buddies, Randy Steck, ended up being an electrical engineer, and with his electrical engineering talent, he went to work for Intel Corporation. You know what Intel Corporation does? It builds this computer and the modern world as we know it. So he, my former missionary buddy, he actually did change our world with what he did as an engineer for Intel. And so and we each can have our own opportunities. And part of it, and that's part of what the message was in the easiest $10 I ever made, right? And you never know what happens. When you acquire some knowledge, you actually change your universe, because the universe has that knowledge that you now have, and you can find a way and make a difference in ways that without that knowledge you could not have done.
Right.
And so you never know what that's going to be. And so it just creates a wide expanse of opportunity for all of you, especially as younger people, and even for me as an older person, right? So that's what we do. Okay, I want you to go to your packet. How much time we have left? 5 minutes. I want you to go to your packet. We're going to just get started on this. And where it's going to be is right here. And that's why I want you to get the calculator. In fact, we just may finish up on this tomorrow. Yeah, we had some extra stuff with that TV today, but see, that's going to help all the classes having that, just a little bit better visibility is what it gives us.
And it's something that needed to be done.
Something needed to be done. In fact, since I mentioned, no, it's still pretty good. Yeah. Okay, right here, what we're going to do is we're going to go ahead and set our calculator to 4 decimal point accuracy. And let's do that. So I have the calculator here. And I'll go to 4 decimal point accuracy. And I'm going to go to float here. And we'll go over to 4. Right? You go to right here. And then what we can do is we'll clear that. And then, so you can kind of divide and conquer if you want to go to fill out the chart. In fact, that could be the last thing we do today. So what I want you to do is take this x cubed minus 8 over x minus 2 and plug in a number. So I'm going to go ahead and do that. I'm going to take 1.9. So I'm going to put 1.9 storage x. Okay, 1.9 storage x, right? Then I'm going to take I'm going to go ahead and put, is it x cubed minus 3? Minus 8. X cubed, oops. Let me go ahead and, got the wrong thing. So x cubed minus 8 over x minus 2, right? And so I go ahead and put that in here, and I get that, and then we can go ahead and get that exactly what it is by going to math decimal, right? So 11.4100, right? So this is going to be 11.41, and then I want you to fill in this table for all those things. You see what I'm saying?
The back of the second, that's the first page.
What did you do? I got 1141 over 100.
Yeah, but he just made it up.
Yeah.
Oh.
And so you do it for all these things. You take 1 point, and then if you plug in 2, you're going to get undefined or something like that, right?
So, okay.
And you're going to have this filled in for everything. This one right here should be 12.59, is that right? Is 2.1 12.59?
I don't know, Mr. G, we haven't made it there.
Anyway, this is some work for you to do, so you can do that. We're going to come back to this tomorrow and hit it, okay? Did anybody get 2.1 yet?
I got it for
12.61.
12.61, okay.
for 1.75. I got 169 over 60.
12.61, let me change that. So what we're going to do tomorrow is we're going to finish filling out this table, and then we're going to have a discussion about what that means, okay? That's what we're doing. For this one here, error, okay, what's it say? Say undefined or error? Just say error. Error, okay. Error.
Error's not good.
Error, okay. So we're going to just come back to this tomorrow. That'll be to give you enough decimal places for a lot of decimal places. That's all.
To give you enough decimal places.
Yeah. So anyway, we'll just leave it like that.